So this is example 26. So y equals x cubed. So this is your graph y equals x cubed. Okay, and I'll draw the graph y equals x to the third. X power 1/3, like that. Okay, so you should be able to see that these are inverses of each other. Maybe you can, maybe you can't. Let's put in the other line, y equals x, like that. So you see that green line is your line y equals x, and you notice how everything is symmetrical about that line. So this line cuts down through what seems to be through the center of a diagram, doesn't it? So let's put in a 0.28. Like that. And we'll label it 28. So this is the 0.28. This is on the graph y equals x cubed. Okay, and this is the y equals x to the third power. So 28 will reflect down a 2. Okay, there it is. So you can see that this 0.28 becomes a 2 on this graph. And if you choose some more points, you'll see that that's true everywhere. Now, what you could do, what they do in the book to show that these are inverses of each other, we do a composite. So what we'll do, we'll put x 1/3 inside x cubed. So you'll end up with y, let's see if this works, y equals x to the third let's get out of there, power 3. Let's see if that works. You can see what happened there. 3 and a third cancelled, and you get y equals x, which is this line here. So this is one way we can test whether these two functions are inverses of each other. So we do the composite of that. And we can do the opposite. We can put x cubed inside this one as well. So that might be easier to do by hand. But when you do that, you'll get the line basically y equals x, isn't it? Because if I type in y equals x, you won't see it. You see, it's the same line as these two are the same line, because 3 times the third is 1. So this is one way we can check whether these are inverses or not. Okay, use the inverse function property to show that f and g are inverses of each other. And I'll draw a sketch of this in a minute. So you've got x is x minus 6 and gx is x plus 6. If you want to show that these are inverses without trying to draw the graph, we just do the composite in both directions. So we have f gx. Okay, so this is telling you to put g inside f. So we'll put it in here. So you'll get x plus 6 minus 6. Okay, so you're going to get x, which is good. That's what you should get. And then we do the opposite. So we do g fx, like that. So now we put f inside g. So we'll go the opposite way. So we'll put the f function into the g function here. So you'll get x minus 6 plus 6. Cancel, you get x. Good. So that shows that fx and gx are inverses. Okay, you could also just call that f inverse x now. You could just change the name if you want to show that these are inverses. So if you are going to graph them, so let's take a look and just check they are actually inverses. This will be quite rough. So we've got x minus 6, which is the f function. So that would be going through minus 6 and like this. Okay, so this is the function fx. Okay, and then gx is x plus 6. So same slope, but the y-intercept is 6. So that would be up here. Like that. So that's looking good, because if we put in the line y equals x, which we have been doing in the past. We'll put that in there. You can see it's right in the middle, isn't it? So they do look to be inverses. So that means that, for example, this point will come down to here at a right angle. And for the same distance, it will come down to this point. Okay, so if fx is, let's write that down as x minus 6. So if x is 7, you'll get 7 minus 6, which is 1. So y would be 1. So this would be the point 7, 1. And on this equation, it would be 1, 7 using the g function here, 1, 7. So again, the variables, the x and y just swapping, 1, 7 to 7, 1. So this is how you show that these are inverses. So let's look at this one. I might let you do C by yourself. So let's try this one. So we need to check fgx is the same as gfx, which should equal x. So that's the important thing. Both of these should equal x, both of these composites. All right, so we'll do fgx first. So fgx. So we're putting our g function inside the f function. So your g function is here. Now put that into your f function here, there. So you've already learned composites, so you should be able to do this. So we'll have 2x plus 5 on 2 minus 5. So if you want to simplify this without expanding, that 2 will cancel this 2 because it's a multiplication, so it will cancel out. So you'll get x plus 5 minus 5. 5 minus 5 is 0. You'll get x. Good. Okay, we found x. So now we do it in the reverse direction. It should work. If it works in one direction, it should work in the other direction. So let's try that. So that would be gfx. Okay, so now put your f function into your g function here. So you'll get 2x minus 5 plus 5 on 2. Okay, so your minus 5 plus 5 is going to cancel, isn't it? So you'll get 2x on 2, which is x. Good, finished. So we can say, therefore, fx and gx are inverses of each other. So we want to put gx into f. So we take our g function and put it in here. Just replace x in the f function. So you have 3 minus bracket 3 minus 4x. Don't forget your bracket on 4. Okay, so you're going to get 3 minus 3, and by expansion, this will be plus 4x on 4. The 3 minus 3 would be 0. Okay, and so you'll get 4x on 4. That will cancel to give x, which is good. So it's looking good in this direction. But then we should also check f into g, which should work as well. So let's put your f function, which is this one, into the g function, which will be in here. So we'll do that. So you get 3 minus 4 bracket 3 minus x on 4. Okay, like that. So what about this one? So that 4 will cancel with this 4, but you still have a minus sign here. So 3 minus 3 plus x by expanding the negative sign here. I just cancelled the 4 here. So 3 minus 3 is 0, and you'll be left with x again. Okay, so that's good. So these two graphs are inverses of each other. So therefore, fx and gx are inverses of each other. So that's how you check whether two graphs are inverses without graphing them. Okay, so very useful. Okay, for that one. So let's go back to question 1, and I'll re-explain this a little bit. Okay, so we wrote the rule down yesterday. So the rule is if, we can write it as an if statement. So if FA equals B, then F inverse B equals A. So in this case, we see how they're swapping. So for example, if F2 equals 3, so if you put 2 into your function, you'll get a 3 output. But if you put your output, then F inverse 3 equals 2. And you just notice how they swap around. That's the main thing to notice here. So that means that you could say that the x value of your function is the y value of the inverse. So this is one way you can think about it. So think the x value of the function equals the y value of the inverse function. And we know that because we're swapping them, aren't we? So 2, 3 in the function becomes 3, 2 in the inverse function. So this is a useful way to think about this. So the y value of the inverse function. I would take note of that somewhere, because that's really what this is telling you here. So the x value of your function is 2, becomes the y value of the inverse function. And the y value of your function is your x value of your inverse function, like that. That's all it's telling you here. It's the same thing. So here, the x value of your function, which is 2, becomes the y value of your inverse function. So F2 is 7, F inverse 7 is 2. So just note how they're swapping here. This goes here, and this 7 goes here. Okay. F inverse 3 is -1. F minus 1 will be 3. Again, just swap your y value, which is this one, and this is your x value. Okay, so this is like x and y, and this is like x and y here. So your x value of your inverse is the y value of your function, like that there. And also, your y value of your inverse is the x value of your function. So they just swap around. And we also did the same idea for question C. So the x value of your function becomes the y value of your inverse. And the y value of your function is your x value of your inverse. It's quite simple, isn't it? You're just swapping the two values, because that's actually how we drew the inverse. Now this one, so this is the y value of your function is equal to the x value of your inverse. So this number here equals 3 in the same way that we did question C, but now we have to find x. So this means that therefore 5 minus 2x will equal to 3. So 2x equals 2, x equals 1. X must be 1 in this case here. So that's what it's asking you to do there. So that would be 1. X would be 1. Okay, and this is the same idea. Let's just do one more because I want to show you some other stuff. So this is a part of a quadratic, but only when x is greater than -2. So the y value of your function is here, is equal to the x value of your inverse, which is here, right? So we can say, therefore, x squared plus 4x equals 5. Now, this is a quadratic you need to solve. So x squared plus 4x minus 5 is 0. So this will be x plus 5, x minus 1 equals 0. So x can equal -5 or 1. But notice here, x must be greater than -2. So there's only one answer, which is 1. You need to follow that there from the original question. Okay, so in this case, x is 1 because x can't be less than -2. And the same idea on this. This is your x value. This is your y value. In your inverse, these will swap. So now this will become the y. So the y value of your function, which is here, is equal to the x value of your inverse. So you can see here, you're going to get another equation. So x plus 2, x minus 4 equals -3. Cross multiply that. So x plus 2 is -3, x minus 4. Expand here. -3x plus 12. This will be 4x equals 10. X will be 5 on 2. So in this case, we found the value of x, which will make this an inverse. Okay. So I should highlight that. So if x is 5 on 2, put 5 on 2 here, 5 on 2 here, then we'll have a correct statement for the inverse. All right. So that's how you do those. So let's go down. Now, this is probably the most important thing you're going to do. And we've got about 20 minutes. So let's have a look. So here it says for linear functions and other harder functions, we can use a method called variable interchange. Notice from the previous section, we got the inverse function by swapping the x and y values. We can do the same here using the functions. So I'm going to redo this here so you can watch here. So fx, let's say fx is 2x plus 3. Okay, it's a linear function, but it works for any kind of function. So what we'll do, we'll let that equal y plus 3. Okay, now what we do, remember when we find an inverse, we swap x and y, don't we? We swap the two values around. So in this case, we're going to swap the x and y in the equation. So swap x and y. So you'll get x equals 2y plus 3. Like that. Okay. But now we need to rearrange it. So let's rearrange that. You'll get 2y equals x minus 3. Okay. But now we want to get rid of the 2. So we divide both sides by 2. Cancel. So you're going to get y equals x minus 3 on 2. This is your inverse function. So we can let that equal f inverse now. You could call it gx, but we want to be clear it's an inverse. So it's the inverse of fx, which is here. So that would be equal to x minus 3 on 2. That's all you need to do. You swap x and y here. So your y equals 2x plus 3 will become x equals 2y plus 3. So just swap where x and y are. then you need to rearrange. I should have written that there, rearrange. So we rearrange the equation to be y. And this is equivalent to your inverse function. So if we graph them, we'll see that they're inverses. We may do more on that another period. We'll calculate and then we'll graph and check if they look okay or not. Okay, that's another linear function. You could write that as a half x minus 3 on 2, can't you? That would be the same thing. So these are kind of hard to do by graphing because when you get fractions in your question, they're kind of difficult to graph. So we don't normally read the equation from the graph, especially when you've got fractions like that. Okay. So this one, I'll show you this quickly because it's not a very important thing for now. Now, remember what I said here. This is the very long way to actually do this question. Okay. What they did here, or what I did exactly what I just showed you. You write your function, you let y equals minus 3x plus 5. Then you swap your x and y to get x equals minus 3y plus 5. And then I rearrange it to this. Okay. So this will be your inverse function here. And then what I did then is I put the minus 8 into the inverse function. Okay. And I got my answer 13 on 3. But you notice a quicker way to do that, isn't there? Because we know that the y value of the function is equal to the x value of the inverse. So all you had to do here was go minus 3x plus 5 equals minus 8. So minus 3x equals minus 13. X equals minus 13 on minus 3, which is 13 on 3. Done. Finished. So you see the difference in the amount of work. For this question, I could have done it this way and got my answer down here, right? But otherwise, if I don't want to do that, I can use the previous inverse function rule and do it this way. So this is the fast way. This is the fast way. I should highlight that too, which is here. This is the fast way. This over here is the slow way. Now this way, the slow way can sometimes be very difficult or nearly impossible to do. So the fast way is a very good way to learn how to do this problem. So if you're given the function and I want to calculate this, I would do it this way instead. Okay, but this is a very slow way to do the problem. Okay, I'll explain how to do this one. You don't have to copy because it's on here. So you've got a function, fx equals x plus 1 on x minus 2. Now this looks kind of difficult because you're going to get 2 x's here. You have 2 x's. So let's see what to do. So we let this equal y again. So y equals x plus 1 on x minus 2. And we want to find the inverse function. This is my goal. This is what I'm trying to find. This is my function. I'm trying to find my inverse function. So the first thing I do, I just let the function equal to y because that's what we normally do. And now we swap x and y. So now we've changed the x to y and we changed the y to x. So x equals y plus 1 on y minus 2. There. So now we do a bit of cross multiplying. So we'll get x, y minus 2 equals y plus 1. So just multiply up y minus 2 both sides. That's all I did. Y minus 2, cancel that. So now I have this. So now I should expand this here. So I'll get xy minus 2x equals y plus 1. The problem in here is you have two y's. So now we need to group the y's. So group y's. So let's group them together, because I don't want to have two y's. I need y equals, right? So xy minus y equals 2x plus 1. So I bring the y to this side and I bring the minus 2x to this side. That's all I did there. Now you see here, y is a common factor, which is really good because that will give us 1y instead, x minus 1. So factorize out the y here, equals 2x plus 1. And y, therefore, would equal 2x plus 1 on x minus 1. And that's your inverse function there. So this is one of the more difficult problems you're going to get. So I would go back and review how to do this later, because you're going to see this in your worksheet, one like this, okay, where you have to grouping your y's here. And then we take the y as the common factor. Okay, so that's how you do that one. And it's all written here anyway, you can take a look. That's another one. Let's go down and do some. That's the same idea. Okay, so everyone, we can work on this one together and let's see what we get. So we're not going to finish today. We'll do this on the next period. So we've got fx is 3 minus 2x on 4. So let's write that somewhere. On 4. And I want to find the inverse using variable interchange. Interchange means swapping, basically. So when we interchange the variable, we swap the x and y, that's all. So first thing to do, write that as y equals 3 minus 2x. So you're following? On 4. Now this is where we swap the x and y. X and y, as we did last week when we find the inverse. So you'll get x equals 3 minus 2y on 4. So just swap the position of x and y. So wherever you see x, you write y, and wherever you see y, you write x, basically. So let's cross multiply the 4. And that will cancel that one. So you're going to get 4x equals 3 minus 2y. So we need to isolate the y by itself now. So what I would do, I'd bring my minus 2y over and make that 2y equals minus 4x plus 3. You may get a slightly different answer depending on where you move your terms, but they'll both be correct. So then y equals minus 4x plus 3 on 2, which is minus 2x plus 3 on 2. Or this, it's up to you. So that's your inverse. So can you copy that down? I'll give you a minute. So write that down and then think about how you're going to evaluate this now. Okay, there's a couple of ways to do it. We've got f3, and we know the f function already. So we refer to your f function here. We've got f inverse minus 4, and we already have the inverse, so you may as well use this one over here. You can use that one or this one here. But remember, you can also use this function. You can also use the function to do it as well. All right, so copy that method down, because this is what I will expect you to be able to do tomorrow. So F3. So I'll just write it here. So F3 will be 3 minus 2 times 3 on 4. So 3 minus 6 on 4. 3 minus 6 minus 3 on 4. So you may want to use your calculator at the end here. So this is minus 3 on 4. Plus, now we're going to put minus 4 into your inverse. So F inverse minus 4. So put that into there. So minus 4 times minus 4 plus 3 all on 2. So that's going to be 16 plus 3 on 2, 19 on 2. I'll let you work that out yourself, okay? So that's 19 on 2. You can make a common denominator. This will be 38 on 4. So you're going to get 35 on 4, something like that. So I'll let you finish that one yourself. Okay, so that would be the final answer as question 1. So let's go down a little bit. So now we have to show that they are inverses of each other. So now what you need to do, we have our 2 functions, which was 3 minus 2x on 4. That's your function. Your inverse function was minus 4x plus 3 on 2. So these are your 2 functions. You've got your inverse function and you've got your regular function that we started with. Okay, so now you need to do the composite as we did previously this lesson. So you need to show that both of them equal x. And if they don't equal x, you have an error. So that means that your inverse is not going to be correct. So let's do the first bit and you can finish it. So we will do this bit here. So that's telling you to put your function inside your inverse function. So your function is here. And I want to put that into my inverse function. So we take that and we stick it in here. Okay, so just take all of that blue bit and put it in there for x. And you can check this one yourself later. So you're going to get minus 4, 3 minus 2x on 4, plus 3 all on 2. Okay, so let's do that one. So I will cancel the 4 here, but not the minus sign. So I'll cancel the 4. So you're going to end up with minus 3 minus 2x plus 3 all on 2. Okay, just cancel the 4, but not the minus sign. So then I will multiply in my minus sign here. So then you're going to get minus 3 plus 2x plus 3 on 2. Okay, so the minus 3 and 3 will cancel. You'll end up with 2x on 2. The 2 will cancel. You get x, which is what you want. So it looks like that we did this question correctly, but I'll let you try this one yourself. Do that one. And then you should end up with x as well. So this is how we show that 2 functions are inverses of each other. Okay, that's what we're showing here. So this shows that fx and f inverse x are inverses of each other. So if we call that fx, then this would be the inverse. This would be f inverse x. So inverses of each other. So f inverse x is the inverse of the function, and also the function is the inverse of the actual inverse function, if that makes sense. So, okay, that's how you did that. We only have 5 minutes left. So take a look at this one. I'll give you a couple minutes. So these ones you can actually do. So just try this for a minute or two, and we'll finish this on the next lesson. We'll work down these questions. For question A, as I mentioned, we will let this equal y. You don't want to have fx here when you've started moving things around. So write that as y equals minus 2x plus 1. Swap your x and y. X equals minus 2y plus 1. And we rearrange now. So you have 2y equals minus x plus 1. And then we divide by 2. Simple as that. Cancel your 2. So we swap x and y, we rearrange to be y equals, and that will be our inverse. So your inverse is minus x plus 1 on 2. Okay. And you can make that as minus a half x plus a half if you want to as well. But I think this form is better actually when you start manipulating the equations around. So maybe keep it in that form there. Okay, so this question, notice it says x cannot be minus 4. So this is a reciprocal graph, which we'll do more on later. But minus 4 cannot be a solution, remember, because minus 4 plus 4 would be 0. So they do state any value that is undefined for that function. So we do the same again. Y equals 2 on x plus 4. Swap your x and y. X equals 2 on y plus 4. And it looks like we need to cross multiply here. So x, y plus 4 equals 2. Let's expand here. xy plus 4x equals 2. So xy equals 2 minus 4x, or minus 4x plus 2, same. Then we divide by x here to cancel the x from that side. Okay, so that would be your inverse function. So f inverse x equals 2 minus 4x divided by x. Note now that x cannot be 0. So this graph will not be defined for x equals 0. So put x cannot equal 0. Okay, in the same way that these other graphs are shown down here. Okay, so there's always some restriction for these graphs, and this is one of the restrictions for these rational graphs here. Okay, so that's your answer. I think we'll stop there. That means from the next period, we will go to questions C and D. And I think there's probably some more here because I need to talk about these a little bit too. So we will stop there and we will continue from here